Today we're going to walk through a few demos deploying clusters in a few different ways. Then we're going to discover clusters from the OpenShift Cluster Manager. We'll deploy an application in multiple clouds, and finally check out multi-cluster observability in Red Hat Advanced Cluster Management for Kubernetes. First, we're going to deploy a cluster from YAML files using Kustomize. While I'm not leveraging GitOps, defining resources in YAML is the first step down that road. Kustomize will combine the local files, and they can be applied to the cluster as a whole through the API. Once we've created a cluster deployment resource, ACM will then install the cluster using the directions provided. That work takes place in a pod, of course. Now we can check the status of the install by looking at the logs of that pod. First, the image set pod will run, and then the provision pod. By looking at the Hive container of the provision pod, we can see the status of the install. Sped up a bit here. You can see at the end the installation has completed successfully. The OpenShift install process creates a default admin user and a kubeconfig with TLS authentication. Since we deployed our cluster using ACM and the Hive API, we won't have that kubeconfig on our local disk. Fortunately, we can retrieve those from the web console, but if you're living the GUI-free life, you can extract them from a couple of secrets in the cluster namespace. Once we have that kubeconfig, we can export our environment variable kubeconfig to point to that file, and any future commands will be directed at this new cluster. You've seen how easy it can be to create a cluster using the command line and tools like Kustomize. Let's see how to do the same thing in the web interface. We're going to create a cluster on Azure, so let's select our Azure credentials. And as we make selections, you can see the values updated in the cluster deployment on the right-hand side. These resources may be copied and applied later using a GitOps process. For demonstration purposes, I'm going to use a tech preview feature called Single Node OpenShift. This is not yet a supported option, but it targets the edge use case, where every square inch matters. Keep an eye out for this exciting feature. Because it is still an unsupported feature, I'll have to make one change by hand, and that is to adjust my master replicas from 3 to 1. Step 6 allows us to integrate with Ansible Automation Platform for lifecycle events, where we can do things like send a ServiceNow ticket or even send a Slack message to the SRE team. As we saw before, a Hive pod is working in the background, reaching out to Azure to deploy the cluster. After a few moments, once the cluster is fully deployed, we can copy their credentials and log into our new cluster running on Azure. Managed and self-administered OpenShift clusters are automatically visible in the Red Hat Hybrid Cloud Console, where the OpenShift Cluster Manager can be used for basic cluster management tasks, including assignment of entitlements. ACM 2.3 adds the ability to detect and import these clusters. It starts by creating a credential to allow ACM to authenticate to the OpenShift Cluster Manager using a token. We're going to name our credential Red Hat and store it alongside the other secrets for ACM. To get our token, we need to visit console.redhat.com. Copy the token provided, and save it to our credential list, granting access to AWS, VMware, Azure, and now OpenShift Cluster Manager. Now that the credential's in place, we can create a discovery rule to decide which clusters in the console we find interesting. We're going to focus on those that have been active in the last 7 days and select any version of OpenShift. Now let's see what clusters have been discovered using our credential. First, in the Cluster Manager, we can see there is a 4.83 cluster on AWS. Any managed clusters, including OSD, ROSA, and ARO, would also have been visible here. Going back to ACM, we can see that the cluster was discovered, and we can now import it. To authenticate to the cluster, we'll provide a kubeconfig. This will allow ACM to deploy a clusterlet. This clusterlet will reach back to the ACM hub, establishing a trusted relationship. After a few moments, the cluster will be fully registered, and ACM will automatically apply some labels, which you can later use for applying policies and application subscriptions. Another feature accessed from the OpenShift Cluster Manager is Red Hat Insights. Insights analyzes telemetry data to provide you with actionable intelligence pertinent to your specific environment. In this case, we're being informed our Prometheus metrics are using ephemeral storage, which will not persist beyond a pod restart. I don't care to remedy that for this demo environment, but that is very valuable information you wouldn't want to overlook in production. Let's talk about a couple of other new features in ACM 2.3. Cluster sets allow you to group clusters together for the purposes of RBAC and networking with Submariner. For this demo, I'm going to focus on cluster pools. They exist to provide rapid and cost-effective access to OpenShift clusters on demand. Clusters in a pool are hibernated to save costs when not needed. When a cluster is claimed by a user, another cluster is deployed to replenish the pool. When the cluster claim is released, the cluster will be destroyed. This may be a great solution for capacity bursting, continuous integration and development environments, or even training. Let's deploy a cluster pool on the command line. We already have an Azure cluster pool in a namespace called Edge Pool. Notice that each cluster deployment also has its own namespace. So let's add an AWS pool of 2 clusters. We're going to use Kustomize again. You can see it requires a single cluster pool resource and a few secrets. So let's apply the Kustomize build. After applying the AWS Edge cluster pool resource, you can see there are 0 of 2 clusters ready. And there are 2 new namespaces for the 2 pending clusters. We can see all the cluster deployments, where they are deployed, and their power state. Let's go check the web console for another view of this same thing. Claiming a cluster is pretty straightforward. Just click Claim Cluster next to the pool, enter a name for your claim, and wait for the cluster to restore from hibernation. I cut the wait from the recording. Once the cluster is restored, you can see the credentials are retrievable right from the screen. So now we have managed clusters on AWS, Azure, and VMware. By the way, the 2 clusters with Edge in the name are from our cluster pools. So let's deploy a Pacman application to all 3 of these clouds. Applications are deployed from channels that track object buckets, Helm charts, or Git repos. A subscription deploys an application to a cluster through the use of a placement rule. So let's look at our Pacman subscription. You can see we're tracking a Git repo, tracking the main branch and the Pacman path. On the Pacman path, we can see there's a customization YAML. Kustomize makes it really easy to store your Kubernetes dependencies in Git. In the editor, we can see the details of the application in YAML. Here, the subscription defines exactly where to pull the application from, and the placement rule defines where to deploy the application to. We can even define when or when not to deploy changes to an application. Nobody likes Mondays. Now, if we scroll down to the topology view, we can see a visual representation of the application and all the associated resources. 2 clusters are already subscribed since they match the placement rule looking for usage equals development. They would be the Azure and the demo cluster. From the route resource, we can see the 2 routes for 2 instances of the app. So let's check it out on Azure. Let's eat some ghosts. Actually, I just remembered, I'm not very good at this. Alright, now what if we want to add our application to Amazon? How hard could that be? Go into the details of the cluster. All we have to do is edit the labels, add usage equals development, Right away, this will match the placement rule. Go back to our application, we can see already 3 clusters are associated. We still have a warning because the app is not fully deployed, so I'm going to speed this section up. Okay. Now we can see the route to all 3 clouds. Let's try to eat some more ghosts. I'm going to do better this time. Okay, maybe not. ACM brings a single pane of glass to your entire cluster fleet. ACM enables search and discovery across all managed clusters simultaneously. In my demo environment, you can see I only have one application defined. By clicking into the search, shows all the related resources. For example, you can see the Pacman application has persistent volume claims for MongoDB on each cluster. There are 6 pods for the application across all the clusters. I can dive down into one, see the details in YAML. For example, this pod is running on AWS. I can also dive into the logs. In addition to this comprehensive inventory, the ACM Observability add-on will aggregate Prometheus metrics from your managed clusters, enabling centralized dashboards and alerting to third-party apps like PagerDuty or Slack. So let's dive into Grafana. From this dashboard, you can see the relative utilization of each cluster. The capacity is readily viewable. Notice that this AWS cluster only has 4 cores and 16 gig, while the Azure cluster has 8 cores and 32 gigs. That sounds like trouble. This dashboard helps you determine if resources are being optimally allocated. Developers make requests for resources, and sometimes they aren't very accurate. This is saying the requests have been made for 250% of the cores, while 90% of the cores are actually being consumed. In this case, we're hampered by the fact that this cluster's capacity does not meet the minimum requirements. So let's check the demo cluster. Okay, that looks like things are closer to being right-sized with 12 cores. Requests are within 17% of the utilization. Let's see how much our Pacman app is gobbling on each cluster. This dashboard breaks down resource usage by namespace, by cluster. After focusing on our application namespace, we can flip through each cluster. Each instance is equally low as expected. So let's look at one final dashboard. This dashboard lets us view the utilization, saturation, and error rates across each of our clusters from one pane of glass. The hub cluster is largest, so it's more interesting to look at. I've only scratched the surface, but I think you can see running multiple clusters, possibly on multiple clouds, would be very difficult without this level of coordinated observability.